So the things the topics that I work on are soft actuators and electroactive materials. So those are enabling technologies for haptics. I believe there is a lot of applications. I hope there is a lot of applications of the technologies that we have developed that can be used in haptics. So I'm here I was very happy of this invitation because I think it's a good chance to connect with the haptics community and actually have an exchange on how we can those technologies could help what you're doing in haptics and what we can learn from all the experience of this very exciting community. I'm going to talk mostly about the things that you see on the left of the screen, that are artificial muscles driven by fluids. And just at the last few minutes, I will also present a bit about the electroactive grippers that we developed in the company that I'm driving. I'm trying to find the timing because otherwise I'm going to be hard. Okay, they might be interesting for haptics as well because they are actually electroadhesion, and electroadhesion has been used already for haptics. We did some studies on combinations of electroadhesion and contact mechanics, where I believe we can learn something that can also be applied when we use electroadhesion for haptics. So I just founded a lab, so let me advertise a bit. At Politecnico di Bari, I became associate professor. Politecnico di Bari, for those who don't know it, it's in the heel of the boot of Italy, so it's kind of, I like to say it's the California of Europe. It has the best weather in Europe. It's a beautiful place on the coast. It's in Puglia. The city is you can see it in the picture. So I put together a small group over there. I received last year, I was lucky enough to get an ERC starting grant that was then used to kickstart the lab. And the name of the lab is Robotic Physics. It's a bit of a fancy name that perhaps at the end of the talk will make a bit more sense. We'll say later what I mean by this, but kind of the motto we use is that we use physics to hack the laws of physics, which doesn't make any sense. But the main point is that by using actuators and robotics at small scale, we can now kind of create devices that if you look at them from far away enough, they kind of seem to disobey the laws of physics. Like we make tubes, for example, that don't obey Bernoulli's laws. And that's actually true if you look at them from the outside, from far away. Then if you go inside, of course, physics make perfectly sense, but then depends on your perspective. And that's kind of the take and the vision of the lab. The context where we work is in what we call robotic evolution. So, well, you know this well, I guess, but just a few words, since this is a haptics community, and I think it makes a good point, this evolution of how robotics can meet haptics. So robotics started with industrial robotics, where the key word was separation. There was a cage between the robot and the human, so no contact, no interaction. Today, we have service robotics that is transitioning from university to the market. So we can now buy robots that can share our same floor, our same environment, and we can actually interact with them. So the keyword is interaction. And now most of the research is focused on what we call human-centric robotics. And that's very much connected to haptics, where there is no distance anymore, no separation between the robot and the human. They're not two distinct entities anymore, but robot and humans can actually be the same entity. So the robot can be wearable, can be implantable, can be something that the human has on his body, on his or her body. A few inspirations, a slide about a few inspirations for this vision. On the left, you see the radical atoms by the Tangible Media Group at the MIT Media Lab that I work with. And here the concept was that we can make the digital world emerge into the physical world. And so there are a few examples of objects like a table that has been hacked and made kind of robotized so that they can move and they can create an interface between physical world and digital one that is, in this case, is part of the environment that the human lives in. Then we have like the miniaturized soft actuators of Herbshays at EPFL, that are wearables, where you have tiny actuators that then create a rich haptic experience or interactive experience. So it can be kinesthetic or cutaneous haptics. And the fact that you made the actuators small, I think, is a key point to make haptic experiences on wearables pretty rich. Then, well, you will tell me, you know better than me. And at the end, on the right, you see the active wearables by Suzumori's group. I like those, and there is a lot of these in my talk and in work that we do, because those are fiber-based actuators, and I believe fiber form factor is very helpful when we want to make, well, when we want to make wearables. It's kind of obvious, like it's not something that it's not an especially brilliant idea, because everything we wear is made of fibers. But also those devices are easy to make, scalable, and I think that's another essential point that we try to, and it's a direction we try to go towards, that we want devices that are cheap, that are flexible, and that they can be scaled up, so that we can make whole body suits. We can make building blocks that then people can use to build robots and haptics. So the transition that the approach that lab is taking is to transition from electrical motors to what, again, we call robotic physics. So first part of the talk will be about explaining what this means by presenting you what are those robotic fluids we work with. And there are 3 examples of these that are like self-pumping tubes, so tubes at the end that can move a fluid inside them by applying an electric field, that they can be used for heat transfer. So having fabric made of fibers that can move heat from one region to another one. And electrofluidic fibers, so again, fibers that can contract when you apply an electric field to them. And then at the end, just a few words on tunable adhesion, so how we can hack contacts by means of an electric field. The whole point here is that we want to have physical devices that we can program, where we can put some autonomy, some intelligence in them, and they can behave not as they would just naturally by following the laws of physics, but we hack those laws so that they can work as we program them, so that we can use them for robotics or haptics. The first part will be about robotic fluids, so on the left here, and I'll start with this video that I have stolen from Clone Robotics. I like it because it shows a robotic hand that is fastly moving. It's not so fastly moving on your screen, but it's fastly moving with a bunch of fluidic actuators in the forearm that are all packed over there. So you can imagine that if you had electromagnetic motors, it would be hard to know where to put those, where to connect all the pulleys and the wires. So it would be a hard device to integrate with all these degrees of freedom. But now it's in this case, instead, they can all be nicely packed inside a space that you generally don't see. Like you put a sleeve on the forearm, you don't see the muscles anymore. But I like also of their video that they didn't hide the jungle of valves and pumps and fluidic components that they need to drive this hand. So there is clearly a problem to be solved there, because if we want to scale this up to a whole robot where there is 2 arms and legs and many actuators, then where do we put all these devices? And that's kind of the point of our research has been to try to miniaturize those devices, making them embedded so that we can have we can have wearable devices and portable devices that can use all the advantages of fluids, all the things that fluids do in biological systems and in well, that engineers use them for, like heating, heavy work, fluid circulation in the body, all these properties of fluids. We would like to transport them into portable devices, into wearable devices. And to do that, we need to basically get rid of the large electromechanical pumps and compressors and replace them by something that is we call solid-state soft pumps. A lot of this work has been done during my postdoc at EPFL in Herbsch's group, where Thomas is also working now. And then the final part is instead the ERC starting grant that started just this year, basically, so just a few months. So what are those? The working principle that we mostly use for doing so, what does it mean? Solid state soft pumps first. It's a funny name because when you have liquids, you are not solid state. But what we mean by it is that the mechanical parts of the device are not moving. So we are transferring directly the energy from an electric field into the fluid motion without having any moving mechanical part, any vibration, any lubrication. And this is, for us, is a kind of a parallel with the electronic revolution, where we went from electromechanical relays to solid-state transistors, because now we can make devices much thinner. I won't go into the details of the physics, but mostly what happens is that we have an electric liquid that gets ionized in contact with the electrodes and then transported. So we apply DC electric field and the liquid moves continuously. So by that we could build the first example of a solid-state pump made of elastomers. So it's a tiny device, all compact and stretchable, and it can actually move fluids. I actually have a few devices. Let me. we like tangible. So we showed that we could drive a soft actuator with this pump. So we took a popular kind of soft actuator that was around in soft robotics, very much used in the old days. Those are new nets, and we stuck one of our pumps to it, and we showed that we could actually make it untethered, so without any pump from the outside and fluidic connection. This was a big encouragement for us. It showed that it was possible to use those solid-state pumps to drive soft actuators, but the performances were still this was pretty slow actually. So we're encouraging, but not there yet. A comment on voltage, you'll see those are all high voltage technologies. That's often a concern for wearables. I'll put a comment out there on this, and then we can discuss it later if you want. I don't believe it's really a problem because the currents are so low that those are not dangerous. So even if you touch the exposed wires, nothing is going to happen because the power supplies that we use have intrinsically a very high impedance. So there is no way they can output an harmful current. So I think it's more a perception issue than a real issue. And also the electronics, we managed to make it super miniaturized now. So it's like a smartphone. So again, I don't think that's a limit. So this was the first work that we did in 2019. It was a big team effort. So big thanks to everyone who contributed. And we managed to publish this in Nature in 2019. So it was encouraging. We decided to move forward. And what we wanted to do was to scale this up. So now we had a pump that was kind of a building block. And the idea was to connect them with soft actuators that would also be scaled up easily. So we got in touch with Professor Sudimore in this group that they were making these thin McKibben actuators at large scale. So McKibben actuators, I guess you know how they are made. They are basically rubber balloons, like thin, long rubber balloons where you put a braid on the outside to direct the formation. And when you pressurize this, instead of just blowing up as a balloon, it's going to expand radially a little bit and contract as you would like a muscle to do. And good thing is that they could manage to make them small diameter and very cheap to make. So they could make many. So we started coupling them, and this was encouraging. But again, performances were not there yet, especially on the pump side. But it showed us that we were going into a direction where we could have a soft actuator that was small and modular and could be scaled up to do, for example, whole body haptics. So the step forward was to improve the pump actually. So we started thinking, so can we make this even more compact? And actually, can we make this into the most essential element that you need in fluidics, which is a tube? Whenever you want to move a fluid, you need a tube, right? So if we could make a pump that was also a tube, then we would remove all the elements required generally to move fluids around, so pumps and valves. And this would be actually a big step forward. So we actually did this. We took the geometry that I've shown you before with interdigitated electrodes and wrapped them around an axis and created a spiral-shaped pump. So we have two electrodes that have spiral shape now. So this work was done with Mike Smith and Herb Shea when I was at TPFL. It started when I was at TPFL, then I moved to Polytechnico Dubai. So they did a big part of the biggest part of the work there at TPFL, and I kept helping on closing up the paper when I moved to Polytechnico. But it was started all together as basically the step forward from the pump that is moving around there. And this is like what I believe it can actually change fluidics. So this device is it has incredible performance and is as simple as you can make it. So it's basically just a rubber tube. It's made of TPU. It has two metal wires in it wrapped around. It's tiny and it can move fluids without any external pump. That's why at the beginning I was saying it's kind of disobeying the laws of physics, because if you think about it, it's like a tube with a negative pressure drop. So instead of having a pressure drop, you have a pressure gain. So generally, when you have a tube and you want to pass fluids through it, you need to apply pressure from the outside. In this case, the tube is creating its own sucking of the liquid. So it's moving liquid without having any pressure from the outside. And the principle is the same. So ionizing, deionizing, and well, let's see it in action. So that's a simple demo. You can imagine what's going to happen. So there is the fiber pump that connects to the liquid reservoir, the Petri dish, and then the other side of the pump has been raised so that we can show fluid circulation. That's one of the power supplies I was mentioning before. So this is it's a 6 kilovolt power supply, but it's size of a smartphone. There is a battery inside to drive it, and currents are extremely low. So as soon as we turn on the voltage, then the liquid is moving from one side of the pump to the other one, so we can create fluid circulation and just giving a DC electrical signal to those electrodes. And so the big advantage is in the simplicity, so because we wanted something that we could easily scale up, even more easily than classic electromagnetic motors, because now this is fully solid state. You can easily imagine there is no moving parts one respect to the other. There is no lubrication needed. There is no components that need to be assembled. It just gets fabricated. Now at EPFL, they are making a process to make it continuous in fabrication. So it's going to be just super cheap to make, and so scalability can be actually obtained. In terms of performance, when we published in 2019, 2023, we could reach about 1 bar per meter of length of pump. So, and the longer the pump, the more pressure you can get at the output. And again, this changed completely the way that hydraulic is managed, is designed. Because generally, when you have a thin and long catheter and you want to have a certain output, you need to take into account all the pressure drop. And so the longer and thinner this is, the more pressure you need to apply from the outside to have the fluid move. And this is actually it's a bottleneck for hydraulics, because generally you can't make very long and thin catheters and have a fast response at the output, because you would need an incredibly high pressure at the input that would actually blow up the tube. And here it's completely the opposite. So the longer this is, the higher the pressure we can get at the output. And the flow rate, so the response, is actually independent from length. So it changes the game of designing hydraulics. Now, it's not magic. It has a lot of limitations still, like efficiency has to be improved. It's still pretty low. We don't understand the physics 100%, like in details, like what's the flow profile inside of the channel. There's a lot of work to be done. And also the liquids. Now we can basically just use a few liquids that are oils. They are good liquids to work with because they are non-toxic, low viscosity, commercially available, but still we can't pump water, for example, and we would like to do that. So that's like kind of next steps. Those are, I've said them already. I'm showing this video from the 2023 paper about how we can use it for thermal haptics. So we can connect now those pumps on a cold liquid reservoir on the back of the hand here. And each pump is connected to one finger. So when the pump is activated, now the cold fluid is transported on the finger, and we can basically show thermal haptic sensation. I like about those pumps that they are, well, whenever you move fluids around, there is many things you can do with it. It's not just actuation, right? You can also do thermal regulation. You could transport some nutrients. And on thermomechanical haptics, we are doing a lot of work now with the team I work with at MIT on how we can combine those together, because I think we believe there is a lot of space in haptics for giving sensations that you can't get individually with mechanical and thermal stimulation. But if you combine the two, then you can get some unique feedback, some unique sensation. Again, a point to discuss. So if you think this is true, let me know, and we'll see if those technologies could actually be helpful. So DRC is about, well, all what I said already. So we are pushing forward those building blocks to scale them up and build devices for making fluidic muscles, wearable, thermal regulation, and textile muscles. We also want to push the use of them in textiles, so making them smaller and more compact. So that's what we are doing right now with my colleagues at MIT. So we are making active textiles by combining those with thin McKibben actuators, even thinner than the one that I've shown you before. And we are making them in a different way compared to the group of Suzumori, with a material that is actually more compatible with these liquids. So those are just few preliminary works still unpublished that we put together. So you can see on the bottom right how the system looks like. So there is just one thin pump and 2 thin actuators. So everything is fiber with a fiber form factor, which I believe gives a lot of freedom, and everything is cheap and easy to manufacture. Well, especially at scale. Now there is still some manual work required. And we made the first example of a glove. Now it's kind of a bit more advanced than that. So we have 5 fingers moving rather than just 1 finger, but you get the concept. Or active textiles, where you intertwine together those fibers with passive fibers to have textiles that move when you apply an electric field to them. That's an example of a response of 2 muscles and 1 pump. It's now lifting 210 grams. So the performance is quite high. It can make meaningful forces. And the response, this is the real time. So it's a big step forward compared to what I showed before. Now we can get quite good performance. It's moving fast and giving forces that can be perceived on the body. So just one couple of minutes on electroactive contacts. So what I've been doing with research and also now with the OmniGrasp company is to make soft grippers that work with electroadhesion. So we use thin silicon fingers with electrodes in them that polarize the surface of the object and the surface of the gripper so that we can pick them up. What can be interesting also perhaps for haptics is the studies that we have been doing on contact mechanics with electroadhesion. So we have been working with contact mechanics people to understand how electroadhesion is affected by the mechanics, like things like peeling, and we have found out that actually we can transfer a lot of what people know already in the models that people have been developing in contact mechanics. They transfer very well to electroadhesion. So now we understand it quite a lot more, and we can use these models to create new devices. And we also studied zipping, which is the opposite of peeling. That is how these fingers can spontaneously wrap around an object just by using electroadhesion without having to have any external actuator. And I think this is very valuable. Small video showing it zipping on different objects. So you can see that the zipping is quite large. So it moves of the tip is about one centimeter of displacement at the end. But thanks to the fact that it does zipping, this becomes possible even with the simple embedded electrodes. Okay, well, we'll put everything together and made a gripper, but this is maybe not so relevant here. And well, that's basically the end of the talk. Thanks for listening. I hope there was some helpful inputs for you. Let me know in the questions, or if you wanna contact me, I'll be around. And we also have open positions. So if someone is interested in doing haptics using these devices coming from your labs, please let me know, because we have PhD positions that are the deadline is the middle of this month, and then there is postdoc positions that have a longer deadline. Thanks.
Any question? What is the time response of the fluidic actuator?
So if you look at the time response of the EHD, electric hydrodynamics, so the time it gets for the electricity to start moving the particles, that's really fast. We're talking about less than 10 milliseconds. Then the response of the whole system depends on the flow rate of the pump and the volume of the actuator. So giving you a response on that as well, combining the two, we can get a kind of 100 milliseconds. It's reachable, even less than that, for a kind of full contraction. It depends how much you want to contract. If the contraction is more, the actuator is bigger, it's going to take a bit more. So it can be, I don't know, half a second or 1 second. Yeah. Thanks for the question.
I can yell, it's okay.
Yeah.
Really interesting work.
Thank you.
I think when I first saw the fluid pump idea, it kind of matched your description as seeming to defy physics, really surprising. I wondered if you could talk about, there's a lot to sort of understand there from a physics standpoint, but I wondered if you could say anything about energetics.
Yeah, oh, it did, yes. So of course, if we look at it with an expert eye, energetically it all makes sense. So the energy is coming from the electric field and is being transported from the electric field directly into the flow field, because we are polarizing, we are ionizing particles. So there is a transfer of energy because the electrodes are actually jumping from the electrode to the dielectric of the liquid, so to the dielectric particle. So there is a flow of current that is going through the liquid, and then these particles are being accelerated by the electric field itself. So it's actually really a flow of current. It's a resistive base. If you think about it, it's like a resistive base actuator. So I
guess it's not a plasma though. Like it doesn't remain. You don't.
It deionizes after, so you don't get plasma.
Goes for ionized, mobilizing current through your.
Yeah. Oh, I don't know.
Is it water?
Let me go back. So the liquid it has to be dielectric. So it's no water. It's generally an oil. We use fluorine-based oils just because they have a very high electronegativity. And to break the symmetry, we want liquids that have either very high or very low electronegativity, so that they charge at one electrode, They ionize one electron, they do not ionize the opposite electron, they only discharge them.
You know the energetic efficiency for electrical.
We know the global one, and the top we can get now is 10%. And that's so we don't know yet because it's hard to, we don't understand the physics at a very fine, with a very fine grained detail. But my take is that most of the losses are actually in poor fluid dynamics. Because, you know, pumps generally have to be designed very well fluid dynamically. Since here we don't even know the flow shape, we can't actually measure it, we can't visualize it yet. It's hard to optimize the device, the geometry, and how the signal we have to apply to make sure that there is no recirculation, for example. I actually believe there is recirculation inside, and that's where a lot of the energy is going. So the good thing about it is that that can be optimized by learning the physics more and more. So there is no, I mean, there is no thermal effects, like direct thermal effects, and everything is going thermal at the end, of course. But I don't believe there is bottlenecks into increasing the efficiency, but we need to understand physics more to do that, as it has been done for pumps always. So it's not actually surprising for me because pumps have became efficient only the last kind of 100 years. Before it was impossible to make a continuous pump, even with blades, like classic pumps, right? Because fluid always wants to go the opposite way. It always wants to go not against, but with the pressure gradient. We are trying to push it the opposite direction. So whenever it has a chance, it's going to circulate back. Then the ionization itself, well, that takes some energy, but then that energy comes back, because then it's also there is also deionization. So I don't know how much of that is actually lost, but it's a good point also to understand why the two different possible losses.
Perhaps we got time for a last quick question.
Thanks for presentation. About your wearable device, like a globe, sometimes the actuator could be limitation, like a subterge, like pronation or rotation. How do you address that issue?
Sorry, I didn't get what is the limitation. Can you say that again, please?
So if you attach actuator on your fingers, sometimes it's resist your motion. It could be like, how can I say? It's like a obstacle. It's uncomfortable to grasp.
I see. Oh, that's a good point. So on that, there is still a lot to be done for us. Like we haven't gone into as much into like the actual human experience with it. So we tend to make them thin and flexible so that they don't impede movement a lot. But there's a lot of discussion on where those actuators go. Like, for example, for the fingers, we decided not to put them on the finger at the end. After the first test, we put them on the forearm. So pumps and actuators are all on the forearm, and we use tiny wires to connect to the fingers, just not to impede bending, because that could be annoying, as you said, could be problematic for the user. Then there can be also some resistance when these deforms, but there, I guess, the design way is impedance matching. The good thing about those actuators is that they can be taught as variable stiffness springs. So you can go from pretty low impedance to much higher impedance when you pressurize them. So you can design them to have an impedance that is similar to the human body, so or lower, so that it doesn't impede when it's not actuated. And then when it gets actuated, the impedance becomes higher and it actually helps the movement. But yeah, it's very open.